So today we'll be doing an LLM Compressor deep dive. This presentation has been given by the machine learning engineering team, and we'll be walking through the LLM Compressor repository. So LLM Compressor, as you guys know, is a model compression repository which lives under the VLM org. It's primarily used after the training or fine-tuning step to further compress or optimize your model before it's used for model serving. That's kind of like a little bit of an overview on where it fits. Today's presentation is primarily going to be focused on and diving into the deeper components of LLM Compressor in terms of some of the general concepts of quantization, sparsity, and some of the more basic aspects of LLM Compressor. We won't be going through that today. However, we do have a lot of documentation and other presentations that we've given in the past related to that we'll be linking out towards the end. Today's agenda will primarily be focused on giving quick updates on the 0.6 release for LLM Compressor that's coming out soon, updates on the API, as well as the recipe and observer updates and architecture updates. We'll also be walking through a couple of newer features, such as AWQ and FP4 support. We'll also be talking about the OpenShift AI integration that was done as part of Summit. And finally, we'll leave some time at the end for questions. You can also ask questions in the chat, which we'll answer throughout the presentation. But if any some longer questions, please hold them towards the end, and we'll have about 10 minutes or so to go through them. So LLM Compressor 0.6 release will be coming out very soon. And there's kind of four main key features that will be coming out as part of this release. The first of which are compression updates, specifically around speeding up the overall compression that's applied to the model at the end of quantization. We have now updated this to compress the models in memory to significantly reduce the CPU out-of-memory issues that we were seeing for some of the larger MOEs. We've also now made sequential onloading support the default pathway to help significantly speed up a lot of the CPU offloading issues that we've seen in the past for layers that were offloaded to the CPU during calibration. So this is essential for especially some of the larger models when users are basically confined to a small set of number of GPUs. We'll also be releasing a significant number of improvements around AWQ, specifically around the general MOE support, as well as performance improvements. And the 0.6 release will also be the first release which will have FP4 support. So the next we'll start off with Rahul will talk through some API updates. Go ahead, Rahul.
Thank you, Deepika. So LLM Compressor provides two core APIs, OneShot and Train, and both serve different purposes. OneShot API can be used for post-training compression. So be it introducing sparsity in your models or post-training quantization using a relatively smaller calibration dataset. Whereas the Train API itself can be used for fine-tuning large language models, be it quantization-aware training or sparse fine-tuning. Next, we'll take a deeper look into the APIs. Thank you. So this simplified function signature here is from our upcoming 0.6 release, where we made a major update. Essentially, we made some keyword arguments explicit here. All the arguments here are typed into specific data classes, and these data classes represent a logical function within the OneShot lifecycle. Model arguments represent model loading and saving. Dataset arguments handle everything related to pre-processing the dataset, and the recipe arguments define the model recipe. This function signature in the image here does not represent all the arguments. For a complete list of arguments, please click the bottom left link here, and that will take you to a page where we've listed out everything. Inside the OneShot function, the lifecycle goes as follows. We first load the model in the specified precision, be it FP16, bfloat16, and then we patch the save pre-train method to add compression capabilities on top. After that, we fetch the calibration dataset and run calibration through the model using pipelines, during which we also apply the modifiers. At the end, we return the compressed models. All of these terms will be explained later on by Helen and Kai. Let's go to the Train API now. Now the Train API essentially accepts everything that OneShot accepts, plus it adds training arguments on top. Our training arguments inherit from from the standard transformer training arguments. So they accept everything related to training, such as optimizer, the learning rate, But it also adds LLM compressor specific arguments on top. For example, the run stages argument that can be used to run a multi-stage recipe, one stage at a time. Our train API also extends all Hugging Face trainer capabilities. And just like I said, it also supports multi-stage recipes. This image in this slide also does not represent the full list of arguments. Please click the link on bottom left to go to a page that shows all of that. Next slide. Now, all of our APIs, they do allow us to pass an output directory and automatically compresses the optimized models for the users on disk. But calling safe pre-trained explicitly gives us a little more control over the compression. Essentially, we patch the safe pre-trained method to add compression capabilities and extra parameters that gives us knobs to control this compression. This patching either happens directly when users call modify safe pre-trained, or we automatically wrap the safe pre-trained method of the models when bunch-out or train APIs are called. The extra arguments added have things like safe compressed. You can turn you can turn compression on or off, or it has things to control specific parts of compression, like skipping the sparsity compression stats. As large language models are getting bigger, we saw that calculating these statistics was taking a longer time. So these knobs just help you control how compression works. The actual compression, though, that is handled by compressed tensors library and model compressor, which at the end of the day takes a look at what quantization was applied and what are the sparsity patterns present in the model and infers the compressor using that. Next slide. The compressor format really depends on two things: the quantization scheme applied and the inherent sparsity pattern of the optimized large language models. In terms of quantization scheme, it is important to know whether floating point quantization was applied or integer quantization was applied, the number of bits used to quantize the model. Can we pack those or not? Or another thing that is important is if we apply weight-only quantization or weight and activation quantization. In terms of sparsity pattern, if the model follows 2-4 sparsity, which means at least 2 values out of every 4 weights are 0, then we have a special compressor for that. The choice of compressor is represented in the config.json. So if a model is compressed on disk, you can take a look at config.json, and there'll be a format field added inside the quantization and sparsity configs. And they essentially represent which compressor was applied. On the bottom left, if you click on that link, it will take you to a table that shows all different scenarios and the compressor chosen for that. Next, I think Helen will go over recipe and observer updates.
Thanks, Rahul. We've simplified the recipe class and made observer arguments configurable. Today, I'll walk through the basics. What is the recipe class? How is it used? What are observers, and how can we configure them? Starting with the recipe class. In the context of LLM Compressor, a recipe defines a structured, serializable set of model modifications for quantization, pruning, and related tasks. It stores a list of modifiers grouped into named stages, supports a creation from YAML JSON strings, YAML JSON files, or modifier objects. It enables serialization to dictionary or YAML file. A typical usage involves creating a recipe instance from a YAML file or string provided by the user, and then instantiating a list of modifiers from it. This flow is used in lifecycle.py, which is a direct downstream consumer of the recipe class. For the key components of the class, stage is a name stage, for example, train or one-shot or test. Modifiers is a list of modifier dictionaries that would later be instantiated into modifier objects. Modifiers are where the actions actually happen. In LLM Compressor, they each implement a configurable algorithm that alters a model through pruning, quantization, etc., either in one shot or during training to optimize performance, efficiency, or both. Version and args are optional. For the methods, we have from modifiers that actually construct a recipe instance from a modifier or a list of modifiers. Create instance, construct a recipe instance from a string, YAML file, or modifiers. Create modifiers instantiates modifiers via modifier factory class. And YAML serializes a recipe into a YAML file, optionally merged with another recipe found in the target directory. Here is an example. This YAML recipe includes a single stage, the quantization stage, with a quant modifiers group. Inside this group, we define a smooth quant modifier and a quantization modifier, each with their own arguments. The recipe class will automatically parse this recipe and validate the structure. Moving on to the observer class, an observer is responsible for analyzing tensors, such as weights or activations, and producing quantization parameters like scale and 0 points. It supports both min-max and MSE observers and works with a range of quantization strategies per tensor, per group, per channel, per token. Observers are configurable via optional keywords arguments passed through the quantization args observer keywords dictionary. These keywords are parsed internally during observer initialization. Supported configuration parameters with their default value include averaging constant, max shrink, grid norm patience, which is used for early stopping. The red parameters are only applicable to MSE observers. In the example shown here, the weights config specifies the observer type as MSE, the current default is min-max, and provides, for example, patience equals to 5 via observer keywords. That's it from me. I'll now hand it off to Kyle for architectural updates.
Or Kyle, do you want to go ahead and start sharing your screen?
Yep. Cool. Hopefully this is working for you guys.
Yep.
Hi all. I'm here to kind of talk a little bit about the core logic of LLM Compressor. We're going to go through like some code examples, and at the very bottom left of the screen, you'll be able to see each of the files as I reference them. So the core logic of LLM Compressor is mostly comprised of like pipelines, as well as like modifiers, all of those like being parameterized by the arguments passed into one shot, as well as the recipes. So yeah, let's get into it. So as Rahul kind of mentioned earlier, one of the major entry points for calibrating a model is through this one-shot API. So this one-shot API basically takes all its arguments and we pass it on to a one-shot class. This one-shot class is responsible for kind of pre-processing the model, so like loading it in, doing any like pre-processing steps that are required, and then also pre-processing the data set as well that you're using to actually calibrate the model. So this one-shot call basically implements a call method, which calls the apply recipe modifiers method. This method kind of instantiates a session and then starts actually inferring which calibration pipeline to use. So a calibration pipeline is basically a method that implements, it's a class that implements a call method, and that call method basically takes in the model as well as the like data loader of all the calibration data that you're using to calibrate the model, and then actually runs that data through the model in order to calibrate it. So I'll talk a little bit more about like which pipeline or like the process of inferring which pipeline is being used. But in the meantime, I'll kind of get started off by describing like what exactly is a pipeline through an example. So this is one of like the basic pipelines that we use in LLM Compressor. This is kind of like the default pipeline that you would suspect or that you would initially implement if you wanted to calibrate a model. So I'll go through it. Basically, this basic pipeline is a class that inherits from the calibration pipeline base class. That's just so that we can provide some like lookup methods. And then also the pipelines are basically augmented through arguments passed by the user through one shot. In the basic pipeline, there's basically nothing to configure just because it's a very basic setup. But these arguments become more valuable when we talk about like the sequential pipeline, which is a little bit more complex. So going ahead here, the basic pipeline kind of implements through like 3 steps. So the first is we take that model that the user has passed, and we kind of dispatch it across the GPU devices to optimize for calibration throughput. So by default, this basically means that you take the model and you split it up across all of your GPUs that are available evenly as possible. And this is kind of the setup that maximizes the throughput of the model. After that, we call something called like a lifecycle callback. So these are basically like the hooks that are implemented in the pipelines. And these hooks are used to basically trigger functions within the modifiers that you pass through the recipe. I'll talk a little bit more about like how those hooks exactly work, but they're basically kind of like events that happen within the pipeline. So you can see here we call the calibration epoch start event. That triggers certain functions within modifiers. After those functions finish executing, we go over into like the actual meat of the calibration pipeline. So this basically takes every batch within your data loader and runs that batch through the model. So this is like the true like calibration process itself. After calibration finishes, we call something called calibration epoch end, which is another hook that triggers functions on the modifiers. For example, like to take all of the calibrated scales that you've just computed and then use those to actually like quantize the modules. So that's kind of like a brief summary of like what a calibration pipeline looks like. Another kind of example here is like our data-free pipeline. So this is the pipeline that we use whenever you have a recipe that doesn't actually require calibration data. And you can see here that this pipeline is really straightforward. There's actually no data to pass through the model. So we just call our calibration epoch start event and our calibration epoch end event. And then that is handled by the modifiers. So that's the basic pipeline. That's the data-free pipeline. Now I'm going to talk about the sequential pipeline. This pipeline is our most complex pipeline and also our default pipeline as well. But it's our default pipeline because it enables a lot of compression flows that wouldn't be previously possible using the basic pipeline. For example, what I mean by that is that if you have like a very large model, for example, if you wanted to calibrate it using the basic pipeline, you basically have to distribute that model across all of your GPUs. For like DeepSeek, that would mean basically taking the whole model and then distributing it across 16 GPUs, 16 A100s across 2 nodes, which is a pretty huge requirement. However, using something called like the sequential pipeline, we're able to reduce those memory requirements really significantly. And I've talked about this previously in like office hours before, and there's also a lot of description in the code itself, as well as like in the examples. But basically, it's a process by which we take one layer of the model at a time, for example, like a decoder layer. We onload that layer onto the GPU. So we move it from the CPU to the GPU, and then we calibrate that layer independently. And then once we're done calibrating that layer, we offload it and then onload the next layer. And then we're using the outputs of the previous layer as inputs to the next layer. So that's kind of like the technique that we're going for here. So really quickly, I'll kind of walk through the code of this sequential pipeline. So the very first step is we take that model and we offload it all to the CPU. And then what we do is we take that model and we kind of trace through it using a sample. And the sample basically allows us to take that model definition that's provided by Hugging Face and turn it into like a frozen graph structure. And then once we have a frozen graph structure, it's easy to take that graph structure and kind of partition that graph into certain segments, i.e. like the layers that I described earlier. And then each of these layers can be onloaded individually. This process happens through, as I mentioned, kind of like tracing. I'll talk a little bit more about it later, but yeah, the tracing logic itself is kind of what enables us to take that model definition and turn it into a graph. Yep, so as I mentioned, it's kind of broken up into different subgraphs, i.e. like our different layers. And then we start calibrating. So all of our calibration happens within this like calibration forward context. This context is basically just takes the model and disables a lot of like the Hugging Face like all of like the Hugging Face functionality that's usually used for like training. For example, like we disable gradients and we disable the KV cache as well. Another thing to point out here really quick is that in the sequential pipeline, we actually disable quantization. So the outputs that we produce, or like the calibration intermediate activations, those are actually activations as if the model itself was full precision rather than being quantized. This is kind of like an aesthetic choice, and we're still researching about like whether or not this actually has a strong effect on the accuracy returns of the model. But just something to keep in mind. The other thing I wanted to introduce here is the class called the intermediates cache. This is something that we've implemented. It's kind of like a useful tool for taking activations and offloading them to the CPU really easily. So you can take your activations, you can put them into the cache, and that basically puts them onto the CPU. So they're no longer taking up GPU memory. And then when you fetch them from the cache again, they're automatically put back onto the original device that you originally put them on. So it's just kind of like a nice abstraction that we've implemented. Cool. Moving on here, here's like the real meat of the sequential pipeline. So here we basically do like a pass through the model where we take our inputs and then feed them through each layer. You can see here through like the subgraph forward method right here. After we've calibrated that layer fully with the entire data set, then we call sequential epoch end, which is a callback, which I'll talk a little bit more about later, but basically triggers all of the modifiers to start taking those calibrated modules and then actually like compressing them or optimizing them using whatever algorithms that they implement. So after we've like calibrated our model and our model has been optimized, then we do one more pass to take the outputs from that layer and then kind of cache them on the CPU so that they can be used as inputs for the next layer. And I'll mention here that this whole process is kind of done batch by batch or like sample by sample. The reason being that you know, if we're able to offload all of the activations one by one, it means that we don't have to load the entire data set into GPU memory. Instead, we just take each batch within the sample, load that onto GPU as we calibrate, and then after we're done, we load it onto the CPU. So at no point is the entire data set loaded onto GPU memory. And this is a huge memory savings at pretty minimal runtime cost. Okay, finally here, we just call our calibration epoch end. For this pipeline, it's more or less like kind of redundant, but it kind of ensures that the life cycle, like the callback life cycle is like preserved, where, you know, modifiers have this expectation that like a calibration epoch start event will happen and a calibration epoch end event will happen. Yeah, that was really quick in terms of like the sequential pipeline, which is our default pipeline now. As I mentioned, like this calibration pipeline is only possible through being able to take like a model definition and turning it into a graph. This is done through like tracing, as I kind of mentioned previously. And in the bottom left, you can see all of the files that implement the tracing. This is all kind of well documented, so I'm not going to talk too much about tracing. But I do want to mention here really quickly is that in the newest release, we've also implemented a kind of pre-processing step called the auto wrapper. This is like a step that basically takes that model definition and actually looks at the code itself, analyzes it as like an abstract syntax tree, and then kind of matches against certain patterns that we know are not traceable within the model. So there's a full list of them in the documentation, and then also looking at the PRs. Those PRs also give a really big description of like how the tracing works, and then what exactly those patterns are that the auto wrapper is trying to match against in order to like maximize the chance that a model can be traced successfully. Yeah, okay, so now that you kind of have a sense of like what a calibration pipeline is, basically something that takes inputs and runs them through the model so that the model can be calibrated and then compressed. I'll talk a little bit about like how these are inferred. So this calibration pipeline class implements like a from modifiers method. And that basically takes in all of the modifiers that you've specified within your recipe and then infers which pipeline to use. So for example, if your modifiers don't require calibration data, the calibration pipeline from modifiers method will infer that we're using it like a data-free pipeline because we don't need calibration data. And then it'll, in the one-shot call, it'll call that pipeline method with the model and your data loader. Yeah, so I'll kind of move on here. The other kind of caveat to mention here is that there's one other pipeline that I haven't mentioned called the independent pipeline. This is basically like a composer of pipelines, like kind of like a higher level pipeline that really the effect is just that if you have like two modifiers, for example, each of those modifiers is going to get its own separate epoch of calibration. So smooth quant, for example, will get its own full run through of the data set to calibrate smooth quant, and then GPTQ will get its full run through the data set in order to calibrate GPTQ. This is kind of like on by default right now, although we're experimenting with having multiple modifiers active at the same time. So that way, you know, if you have two modifiers, you only have to run through the data set once, which will cut down on performance. And we suspect will not actually affect accuracy at all. In fact, it might improve accuracy. So this is just kind of the other caveat to mention when you're using pipelines. So now that we kind of have like a sense of what pipelines are, we can talk about like the callbacks that are implemented in those pipelines. So as I mentioned, like there are these callbacks that are called in the pipelines. For example, calibration epoch start and epoch end. And you might have the question of like, how do we actually go from like a callback to actually, you know, running methods within the modifiers itself? For example, if you're trying to implement your own modifier. The answer is that there are a lot of layers of abstraction that kind of happen here. So, you know, you'll call like a calibration, you'll call like a callback, and then that callback basically calls the event method on the compression session, and then that method will call the event method on the compression lifecycle class. So there's like kind of a lot of layers of abstraction that happened here. But eventually you get to the point where you actually take that event with the event type that you've kind of specified, and then you actually call the modifier itself with that event using this like update event method. There's a lot of like kind of small steps that I'm skipping over here. So things like, you know, validating that the order of the callbacks is correct. So you don't want to call like epoch end before epoch start. Other stuff like there's logic here for automatically incrementing the batch index during training so that like a implementer doesn't actually have to pass the batch index. We can like automatically infer that. And then there's also a lot of like recipe logic that happens here that we're trying to clean up as much as possible. Because at the end of the day, what we really want is we really want to take these like callbacks, and we really want it to just be like a for loop over all of our modifiers where it just passes this data through the modifiers. The other two mentions here are that like there are special events called initialize and finalize. These go through slightly different pathways in order to get to the modifiers, but at the end of the day, it's the same kind of idea where we're iterating through our modifiers with the event that we're trying to call back with. So finally, we're at the point where like we have a modifier and we're trying to implement on it. All modifiers kind of implement these 5 methods. And all of this, you know, the order kind of displayed here is roughly the order that happens, except for on event, which usually happens in between start and end. But you can see here, each of these methods gets called at different times within the pipeline or like within the life cycle. So on initialize gets called before the model is dispatched to devices. So you can guarantee that that model itself is like not split up between a ton of GPUs. On start is another method here where, yeah, it's basically called on the epoch start of like right before calibration starts, or during training. This happens like on the like train epoch or batch that you've specified. Similarly, on end is kind of a similar idea, where like during training, this might happen during like the end epoch that you specified on the modifier. And then for calibration, this just happens like after you've done a full run through of the data set to calibrate it. On finalize is called after on end. So this is basically like a kind of cleanup step that makes sure that the modifier like frees any memory that it doesn't need anymore. And then also like we have like guarantees and assertions here to make sure that that calibration actually was performed correctly. On event is the method. It's kind of like a catch-all event. So like any other kinds of events that might happen get filtered through here. So things like, if you're training and you like calculate a loss or like optimizer steps, all of these events get passed through the on event method. I'll also mention here like the sequential epoch end event that's specific to the sequential pipeline also gets filtered through this like on event method. Yeah, so I'll go really quickly through like 2 examples. The first example is like the quantization modifier. This is like a core modifier that implements like the round to nearest algorithm. Basically, this method on initialize, it takes like a quantization config that the user has specified and kind of attaches that config to the model itself. So it basically like makes sure that like each of the modules that are being targeted like have like a scheme attached to them. And this is like used for future steps. On start is called right before calibration happens. So right before calibration happens, we add a bunch of hooks to the model. And then these hooks basically trigger whenever like a sample is passed through the model. And then this is useful for like calibrating the scales and 0 points, like the quantization parameters. Yeah, that are like specified by the modifier. And then also does a step here to like quantize the weights themselves. On end is called after calibration finishes. So this kind of just like removes all of the hooks. And then on finalize just ensures that on end has been called. Yeah. And so now that you kind of understand the quantization modifier, GPTQ is very similar. It just implements a couple more hooks. So for example, it registers like a custom hook called like the GPTQ hook, which is kind of, which is our hook, which takes in like the activations and then uses them to update the Hessian for the Hessian calculation of the GPTQ algorithm. Yeah, and then like on end, and then also on like sequential calibration epoch end, it actually does the optimization or like compression of the modules using that Hessian that was calculated using the hooks. Yeah, so those are kind of 2 examples of like different modifiers that are implemented by LLM Compressor. And hopefully that kind of gives you a sense of like each of these methods and like the order in which they are called, and then also how you could like use this to implement your own algorithms using modifiers. Finally, I'll call out here, like here are all the different events that are provided by LLM Compressor. So there are a couple that are kind of required by all pathways. So that's like the initialize and finalize method or events. We have a couple events related to like batching. This is like basically only for training. So if you have like a training batch, you can have a start and end event for that. For calibration, we implement our own events. So whenever like a calibration epoch starts, an epoch ends, and then also that sequential epoch end event that's very specific to the sequential pipeline. And then finally, like anything related to like optimizer lifecycle, so things like calculating a loss or the optimizer itself performing a step, all of those events are also implemented by LLM Compressor and are hooked into by modifiers. Cool. So I went through a bunch of information there. And all of the files, as I mentioned, you can go reference using the bottom left there. And then hopefully these slides will be shared out at the end as well. But basically, in summary, we have this like one-shot call. This one-shot call calls all of the pipelines. The pipeline type is inferred from the modifiers. So if you want to change your pipeline type, all you have to do is kind of change the modifiers or the recipe that you're using. Each of these pipelines, when they're called and they're calibrating, they trigger your callbacks. And then these callbacks eventually call to the modifiers. And these modifiers are the algorithms themselves that eventually end up like optimizing or editing the model or state itself. That's like a really, really quick overview of like the core logic of LLM Compressor, but hopefully it gives you a sense of like how you would actually implement and hook into your, hook your algorithms into LLM Compressor. From here, I'll kind of swap over to Brian, and he's going to talk about AWQ, which is one of these modifiers that implements the AWQ algorithm.
Thanks, Kyle. Yeah, so as Kyle mentioned, he mentioned the quantization modifier and GPTQ. So AWQ is another modifier in our repertoire. The original paper, it comes from 2023 to 2024. It's called Activation Aware Quantization. This is a weight-only quantization. So if you ever see any of these things like W4, A16, what that means is the weights are 4-bit and the activations are 16. There are other schemes like W4, A8, W4, A4. but the target for AWQ is W4A16. The quantization loss of the activations is not included in the algorithm, so it could be run, but it would not perform well if activations are quantized. So this leverages a lot of the architecture improvements that Kyle mentioned. So I'll share in a couple slides how it's leveraging the calibration lifecycle and sequential onloading, as well as the quantization mix-in. But from a high level, like what this means for our support for multimodal and MOE models is that we can actually quantize these on single GPUs up to a certain point. In the case for Qwen 330B, which is a mixture of experts model, MOE model, we can run that with only 15 gigabytes of peak VRAM required in about 2.5 hours. So because we're only onloading one layer at a time that we're investigating, we can greatly reduce the amount of GPU memory required. I believe this wouldn't even fit on a single, I think I could barely get it to fit on an H100 before, which has 80 gigs. And then conversely, we had another community user request, Cohere Labs C4 AI Command R+. That's a 104 billion parameter model. I was able to run that in a couple hours with 74 gigabytes VRAM. So this is a larger model, but it's not one that you could even run on a single H100 to generate tokens. It would have to be split or offloaded and onloaded. So I thought that was a pretty cool win in showing like what we can do with sequential onloading without really any of that code living in AWQ. So Kyle, if you move to the next slide. I just want to explain really high level ELI5, how does this work? On the right-hand side, this is our big, long, large language model, where you go in with tokens and you get a token out, but in the guts of it, we have these decoder layers. And what AWQ makes note of is that there are several points in the model where we have something that is scaled by some parameterized weight, and something that is followed by something that is scaled by some parameterized weight. So Kyle, if you click the next, just highlighting that here, our input layer norm or our post-attention layer norm, those have a set of weights that we can scale up and down. And conversely, we can scale up and down the projection layers, which are linear layers. So we're going to make note of that degree of freedom that we can scale these and make use of that to decrease the loss due to quantization. So in the next slide, just a little bit more formally, we have our weights W, and we want to find some diagonal matrix S so that we can take the weights of our post-attention layer norm, multiply them by S, and take the weights and biases of our projection layers and multiply them by inverse of S. So the algorithm will find the best S with a grid search. So it's a little bit more expensive in that it's not just doing a simple backprop or gradient descent. It's actually doing this, I believe, 20 times in a grid. But this is because of that, we can set up our loss function and run through these, find our candidate S's, calculate the loss, find the one with the lowest loss. So on the next slide, I'll just kind of go through. So like that's the high level algorithm. How does this live in the code? This is all in LLM Compressor modifiers AWQ. First, we start with the AWQ modifier. You can see I'm adding the quantization mix in. So when we want to quantize at the end, none of that code has to live in AWQ. It just pulls in the same logic that lives in quantization modifier. And so for our life cycle, Kyle mentioned on initialize, on start, on end. This is how it works with AWQ. On initialize, first we need to find where these mappings occur, and we want the pointers to the actual modules, like the torch modules. So we grab the pointer to the post-attention layer norm. That's what we're calling the smooth layer. And then the gate proj and up proj are the balance layers. And we also need the parent that these live in so that we can calculate the loss. So on start, we kind of, if you can go back, Kyle, just real quick on start, when we add the caching hooks, we need to keep track of certain things. For example, we need to keep track of the inputs that go into the parent so that when we want to calculate the loss, we can do a forward pass through it. And then also with the smoothing layer so that we get the activations which are used when calculating the S, the scales. Next slide. So after we've added those hooks, we'll run through the sequential pipeline, which will actually pass these batches through the model, each layer at a time. it will hit our hooks. We'll get those cache values saved. And then when that epoch ends, we want to apply our smoothing. So this is where we call compute best scale. We just need the mean values of the weights and the activations. We want the parent module, the balance layers, and the actual output of the unquantized model. When we have that, we can do our best scales. This is where the meat of AWQ lives. It's the most expensive part of it, where we find S in our grid search. Once we have that best scale, those best scales, we can just go in and update each of the balance layers. So you can see we're multiplying by S for each of the balance layers, and we're dividing by S or multiplying by S inverse for each of the smoothing layers. Next slide. And then just lastly on end, so this is after everything's run, we want to make sure that we've consumed everything in our cache. So we make sure that nothing has gone wrong. And then we have a few lines here where we're plugging in the quantization mix in. So we actually go in and convert our floating point 16 weights into our W4 int 4-bit int weights. And we remove our hooks. On finalize, we get rid of all that in memory so that if the next modifier needs to run, we don't have anything lingering on GPU or CPU RAM. I think that's all. Kyle, if you move to the next. Yeah, so let me pass it to Divika for FP4.
Cool. As part of the 0.6 release, LLM Compressor now has end-to-end support for NVFP4, which is NVIDIA's FP4 format. What this specifically means is that NVIDIA's FP4 leverages the Blackwell machines for their quantization. Their format specifically does two things. They follow per group size 16 quantization, where each group scale is of FP8, and they also provide which also includes a per tensor FP32 global scale. This is also seen with our activations, where each activation set is quantized on a per group basis of, again, group size 16. But in this case, this is done dynamically, and all the quantization scales, again, here are in FP8. For the activations, like the weights themselves, there's also a per tensor FP32 global scale, just like the weights. So in this case, we're obviously going away from their standard just scales in 0-point format. When we talk about quantization parameters, quantization scales, this is always in on a per group, per tensor, per token basis. And now we're kind of expanding on with FP4, we're expanding to include an additional global scale, which really just has the responsibility of making sure that the quantization scales that we're generating fall properly within the FP8 range and make use of the entire dynamic range. And some of the maths to do that is kind of seen here. So you can see is that when you're generating this quantization scale, you're further multiplying it by this global scale and then clamping it between the min and max of the FP8 values to ensure that the scales that we're generating for quantization properly fall within the entire range. Go to the next slide, Brian. And with FP4 specifically in compressed tensors, we're now supporting two new schemes. So there's NVFP4 and NVFP4 A16. Both of these schemes are now available in compressed tensors as part of the next release. NVFP4 specifically includes both weight and activation quantization, whereas NVFP4 A16 only includes weight quantization. And some of the key things that have changed as part of this is that we've extended some of the key fields that you would have otherwise seen within your compressed tensors config for the models, specifically the strategy and the dynamic field. And all models that are compressed using NVFP4 and NVFP4 A16 will be quantized and compressed using the new NVFP4 packed quantized compressor, which is then compatible with NVIDIA's Cutlass integration on VLLM. Next slide. So some of the changes that we've made, first of which is the dynamic field. So for other compressed tensors models, if you look at their quantization config that's stored when you save the model, you'll be able to see that the dynamic field is either true or false, which basically indicates whether or not you're dynamically generating the quantization scales during an inference or whether or not it's done during calibration and saved to the checkpoint. We've now extended this to include an additional local field, which essentially indicates whether the quantization parameters are dynamically generated. And this is done in order to help differ between the local quantization parameters being generated dynamically, as well as and with the global scales being generated dynamically. So now there's kind of three instances. When something is dynamic, it means everything that you're generating at this point is done on the fly. Whereas if it's false, that means everything is done statically. And this new local indicates kind of a hybrid where only the quantization parameters are generated dynamically. However, the global parameters, which are potentially present, may be generated statically. Next slide. And as part of the FP4 and NVFP4 support, we've also extended our quantization strategies. So historically speaking, per tensor, per channel, per group, and per token were the main strategies that we supported as part of the quantization schemes that are available in compressed tensors. As NVFP4 has a per group and per tensor scale that's generated for both the weight and the activation. And this is basically essentially a hybrid of the two existing strategies. We've added a new tensor group strategy, which basically indicates that we're generating scales on both a per tensor and per group basis. So for going forward, all the models that are generated following the NVFP4 format will have the tensor group strategy saved to the config during quantization. Next slide. And another key change are to the observers themselves. So as we mentioned towards the beginning of the presentation, the observers were created to basically calibrate and update the quantization parameters, specifically the scales and the 0 points. As NVFP4 has additional global scales, we are now extending this to add in the ability to generate global scales during calibration as well. So the user can now calibrate these during calibration, as well as the quantization parameters. Currently, the min-max observer is the only one that gives you the ability to generate a global scale. MSE currently does not support global scale generations at this point. It's only the min-max one, and we'll potentially do this in the next release, but as of 0.6, only min-max is currently supporting this. Next slide. And just to kind of close off in terms of FP4 work, as of the 0.9.1 VLM release, the NVFP4 and NVFP4 A16 integration will be supported as well. So you can then run models end-to-end for all non-MOE cases. And if you don't have access to a Blackwell machine, the models will you can either use emulations, or it'll fall back to use a Marlin integration, which will then essentially just ignore the activation quantization during inference time. We'll be following up with integrations for MOE specifically, and that's the current work that we're currently doing right now. And we'll also be extending to the general MOE support and LLM Compressor going forward, specifically to make sure that just during calibration, we are allowing all of the experts to see at least some data during calibration, so we aren't left in the case where some global scales are essentially empty. And then another kind of piece of work that is going into for FP4, but generally within compressed tensors, is the ability to allow more than one compressor to be active at a single time. And this is basically in order to ensure that in the future, if we want to quantize models that have both FP4 and FP8, for example, active at a single time, the user has the ability to compress with both compressors. Currently, the only choice is to have one global compressor. However, with FP4 and other cases, there may be some advantage of mixing them without having uniform quantization throughout the model. And so this will be something else that we're currently actively working on. It's not part of the 0.6 release, but we should be part of the next release or so. And now I think we'll put it back to Brian to go over an OpenShift AI integration overview.
Thanks, Devika. So yeah, just wanted to share quick, what we've shared so far has all been improvements to LLM Compressor, the software package, but we've also been looking at how we can integrate it more deeply into Red Hat AI's other offerings. So for Summit, we wanted to build a demo showing how we can integrate it in OpenShift AI. This is useful if you're running a series of experiments, different compression experiments, maybe trying different modifiers or different hyperparameters, or trying them over a wide range of different models. That this allows us to run in parallel in isolated GPU environments with a pure Python interface, and allows us to share model checkpoints, logs, resources, results, all in a single place. The screen cap kind of shows a little bit of this. So I can run a single one-shot calibrated run and compare it to a data-free run. The models are checkpointed. It gives us an S3 link where we can download them. It saves results and logs. So it's a nice way if you're running a whole bunch of manual tasks and you're messing around with things like SSH or TMUX or cron tabs to like really automate this and streamline it in a nice shareable way. So the call to action for the research team, if you find yourself doing this and are looking for better alternatives, please Slack me. I'd like to build set of use cases or examples that as an impetus to try to integrate this into some of our compute clusters. This image comes from the blog post and POC demo that we generated. The link is available in the bottom right as well. Thank you.
And just to finish off before we dive into questions, in terms of upcoming work that we're working on, so after the 0.6 release, we'll be focusing on a lot, some additional features, including transform support, specifically around supporting algorithms like spin quant, and also being able to combine transforms with things such as FP4. As I mentioned, we'll generally be extending our FP4 support to make sure it's well supported for MOEs. We're always working on further improving calibration performance, and we're also now looking just generally to go beyond just compression. That's where we're as we kind of work towards other things such as speculator support.